you have this. This is A complement. X is not here. Then X has to be here. Why? That is because A union A complement is universal set. And we know that every element belongs to the universal set in the discussion. So any X belongs to U, which implies X belongs to A union A complement. So this implies X belongs to A or X belongs to A complement. These are the only two possibilities. Okay. At least one has to be true. Now since it's already given that X does not belong to A complement, so the other possibility must be true. That's why we are getting X belongs to A. From these equivalences, we get A is a subset of complement of A, and this is also a subset of A. Thus we have the first one. Okay. Now after this, instead of going in the natural order, I prove this one because it can be used to prove many of them. If A is a subset of B, then A minus B has to be empty. You see, again you have to prove that some set is empty. So you start by supposing an element in, suppose there exists an element X belonging to A minus B, right? This implies X belongs to A and X does not belong to B. That is just simply using the definition of difference of two sets, right? But X belongs to A means X must belong to B because A is a subset of B. X belongs to B and X does not belong to B. Here you can write the justification since A is a subset of B. But this is impossible. An element belonging to a set at the same time not belonging to the set, because this is empty. So no element can belong to a set at the same time not belong to the set. So that's why our supposition is wrong. That means there can be no element in A minus B. That's why A minus B is empty. Okay, so this part has been proved. Now, how can we use this to prove the other things? You see, the empty set is a subset of any set A. So that's why empty set minus A is empty. So this is a consequence of this. Just like that, if you look at this, any set is a subset of the universal set. So this implies any set minus universal set is empty. So we have got this one also. Okay? And we can use this here also. Any set is a subset of itself. So A minus A is empty. See how nice. We are getting many of these things as consequences of this general one. Okay. Can we milk it more than this? No. These are all we can have from this. Now next, okay, now we have to prove this one. Okay, before proving this, let me prove this one. A minus B is equal to A intersection B complement. You can see it in Venn diagram. This is A, this is B. You already know this portion is A minus B. What is this? The rectangle is always U, which contains all the elements in discussion and all the sets as subsets. Okay. Now this part is A minus B. Now what is A intersection B complement? You have to look at that. First of all, what is B complement? The part that is not in B, right? This is B complement. Okay, and what is the common? What is the common region between B complement and A? Clearly, this part, and that is nothing but A minus B. So from the Venn diagram, we see at least that this should be true. Now we prove it. But instead of no, we have to take elements, otherwise it will become we can prove some of these instead of using taking elements. Sometimes we can use some other results which say that, for example, I have to prove that A minus B is a subset of A intersection B complement. Now A minus B is already a subset of A, but that can be done at an advanced level when you already have much knowledge about these things. Okay, you already have worked a lot of problems like this. At this stage, we start by taking elements A minus B. So now my aim is to prove that A minus B is a subset of A intersection B complement. So X belongs to A and X does not belong to B. Now, not being in a set means what? Being in its complement. So that means X belongs to B complement. Oh, this is rather easy. You see, you can easily go in the other direction also. You assume this implies this implies this, and this implies this. So this is a subset of this, and this is a subset of this, thereby proving that we have this equality. Okay, now why have I proved this one first? I somehow feel that this can be used to prove the other things. Let us see. Okay, A minus the empty set. This can also be written. See, now we are not writing implies or anything. We are just simply working with sets as if they are numbers. So I can write A intersection this. Now I can write A intersection U provided I know this. So since I don't know this, so this proof is actually incomplete. It will remain incomplete unless I prove those things. Okay, those I am coming to them later. Now since A is a subset of U, every set is a subset of the universal set. So the intersection will be the smaller set. If you recall, this is one of the last property, the fourth one about intersections. Okay, so I get this one, although it is incomplete. Why? Because I still don't know that this is equal to this. That I haven't proved yet. So I complete this one in an incomplete way. Like that, I try this one also. So this is equal to A intersection A complement complement. but in this case we already know that A complement is equal to A. So A intersection A, but A intersection A is A. So this one is complete. What about this one? Same, A minus A prime minus A. You can write this as A prime minus A prime. Oh, sorry, I forgot what I am doing. Now, instead of using this one to prove this one, I can take even one more step ahead and I can use this one to prove this one. How? Because in place of A, I can write this. So this is just like writing a set minus its complement. So a set minus its complement is the set itself. In this case, the set is A prime. So this is equal to A prime. So that's how I have proved this one. Okay. Now I am yet to prove these two, right? So this I have to prove in the usual way by taking elements. For the first one, because I have to show that something is equal to empty set, same method. Suppose there is an element x in U prime. This implies x does not belong to U. That is coming from the definition of complement of a set. But by definition, every element must belong to the universal set. So we have arrived at a contradiction and impossibility. So that's why our supposition is wrong. U prime cannot have any element. So U prime must be equal to the empty set. That's how we have proved this. Okay. Now, to prove this one, since every set is a subset of the universal set, I already have this. Conversely, I take an element in U. Okay. Now this implies X does not belong to empty set. Actually, you see, there is no relation, no apparent relationship between this statement and this statement. It is saying something about the universal set that we have chosen, and this is saying something about the empty set. But this is true. Okay. So true statement implies true statement, so the implication is true. So we can write something like this. This is just like the situation where we wrote that which one? Law of exclusive middle. Okay, this is something like that. Now this implies X does not belong to empty set means what? X belongs to the complement of the empty set. So any element in U is also in the complement of the empty set. So U is also a subset of this. So they are equal. So we have proved this. So there is only one thing left to prove, this De Morgan's law. So I have to prove that the complement of an intersection is a union of complements. So I take an element here. This means X does not belong to A intersection B. Okay. Now this in place of this I am writing X does not belong to A or X does not belong to B. Why or? That is because this means negation of x belongs to A intersection B. Okay, and this is equivalent to negation of x belongs to A and x belongs to B. Now, when we come to negation and we have and, the negation takes itself inside, applying itself to the simple statements, and it changes and to or. One of the De Morgan's laws from mathematical logic. In fact, we have carried out a similar argument previously also, in this video somewhere, I remember. Or negation of x belongs to B. While proving that A not equal to B implies A minus B is not equal to B minus A. While proving this one, I have carried out a similar argument. So x does not belong to A or x does not belong to B. That's how we are getting this. Okay. Now x does not belong to A means x belongs to A complement, or does not belong to B means x belongs to B complement. So this implies, since we have or, so we have union. We can also go in the other direction, since here also we have equivalence. So this implies this. This implies this. This implies this because of this. And this of course implies this. So we have proved the other De Morgan's law also. Okay. Now, so that concludes the properties of difference and complements. In Cartesian product also we left out something, and that is A union B cross C. I think that's what it is. A union B cross C is equal to A cross C union B cross C. So to prove this one, now we have Cartesian product, so the general element will look like an ordered pair. So first we show this is a subset of this. So we take, let x comma y be an element in this. This implies x belongs to the first coordinate belongs to the first factor, the second coordinate belongs to the second factor. A union B and because it's Cartesian product, y belongs to C. This implies x belongs to A or x belongs to B and y belongs to C. Using distributive law from mathematical logic, this implies x belongs to A and y belongs to C, or x belongs to B and y belongs to C. And this gives me x comma y belongs to A cross C, or x comma y belongs to B cross C, which further implies x comma y belongs to A cross C. Since we have or, so union B cross C. Conversely, if I have an element here, this will imply this element belonging to this or this. That will imply this. This will imply this because of distributive law from mathematical logic, that has equivalence, that is an equivalence, okay, not an implication just. And then this implies this implies this. So this proves this is a subset of this and this is a subset of this. Hence they are equal. Okay, so we have finished proving the things that we left out in the previous videos. Now, but these are not problems on set theory, right? These are just, we have completed the proofs. Oh, but there is one more thing. Now this I will prove only, if you remember, we proved this thing, right? For finite sets A and B, cardinality of A union B is equal to this. But while proving this, I asked you to prove three identities which look like this. Okay, this is one. Another one is A minus B union, actually four things. A intersection B. Then just like that, B is equal to B minus A union A intersection B. And these three sets are mutually disjoint. This is empty. This is also empty, and this is also empty, right? Now, these again I am leaving to you. Okay, I have already left them to you to prove. So again, now armed with the experience in this, how to prove these identities, because today we have proved many of them. So armed with that experience, you try these things. Now they should not be as difficult as they previously might have been. Okay. So this part I am leaving to you. And also one thing I am leaving to you is remember we defined symmetric difference of two sets also. And I state that for three sets, a symmetric difference, that operation is associative. And I have also mentioned then that this is somewhat lengthy and complicated, and that the symmetric difference, intersection distributes over symmetric difference. These two things are more complicated to prove than the rest of the things we have done today. So they are also left out for now. We will prove this, but in due time. Okay, this is not something that you come across in school. Okay, so far what have we done? These are some unfinished proofs of some properties that we have proved. Apart from this, there are some practical problems that can be solved using set theory, which mainly involves finding out the number of elements in a set. Although the problems, as you look at them, they don't involve sets, but you will come across number of certain types of objects. In such situations, set theory can be used, and in particular that result which calculates the cardinality of the union of two sets, that result is used. And an extension of that result is also used, which goes like this. You see, we already know that if A and B are two finite sets, then we have this. Provided you finish proving the other things that I have asked you to prove. This can be extended to three sets. Okay, and we write like this. Now, this union can be viewed in either of the two ways. You can view it like this, or as the union of A and B union C. Both of them are equal because of associativity of union. So, thinking of it like this, and using this formula, I get cardinality of A union B plus cardinality of C minus cardinality of A union B intersection C. Now here I can again use that formula. But what do I do here? You see, this is a situation where you can use one of the distributive laws of set theory, right? Oh, that one is also, I left it up, right? I had to prove the distributive laws. But now I will ask you to prove that. Okay, since you have seen so many of the proofs, I'll ask you to prove both the distributive laws. Using one of them, here we get this is equal to A intersection C union B intersection C. So you see that this is again a union of two sets. So here also I can use this formula. In place of the first set I have this, in place of the second set I have this. So let me write cardinalities of A, B and C together minus cardinality of A intersection B. What about this one? Minus, you see carefully that there is a minus sign. So whenever you come across a minus sign and it's after that you have to write something, it's always wise to write that within brackets. Cardinality of A intersection C plus cardinality of B intersection C minus cardinality of A intersection C intersection B intersection C. Okay, and this is equal to, I won't have space, so let me continue from here. This is equal to minus cardinality of A intersection C minus cardinality of B intersection C. Multiply these two minuses, you get plus. Now what is this set? This is A intersection C intersection B intersection C. So this is nothing but A intersection B intersection C. I leave it to you to see that these two things are the same. Plus. So here we get a bigger formula. This is equal to this. So if you have three sets, then the cardinality of their union can be expressed like this. Okay. You can increase the number of sets even more. The formula will get more and more complicated. In fact, you can write a formula having any number of sets, but that is less used. I mean, as far as application goes, this is the limit. I haven't seen a problem which involves 4 sets in this situation. There may be some, but if we come across some problem, we have to extend this formula to 4 sets. Although if you can see the pattern, you can write the formula for any number of sets. To remember the formula, I have to write it again. You see, how to remember the formula? Since we have 2 sets as well as 3 sets, let me show you the pattern. First you take cardinalities of single sets, okay, and you always add them. Here also you take cardinalities of single sets and you always add them. That's how you start. After that, so this is plus, after that comes minus. But instead of 1 set, next you take 2 sets. Now since here we have only 2 sets involved, so I write minus, and what do you do with 2 sets? You take their intersection. Here I have 3 sets, so out of 3, 2 sets can be chosen in 3 ways, either AB or BC or AC. So I write minus A intersection B minus B intersection C minus cardinality of A intersection C. Now once you have written that, after that 3 sets come. Since we don't have 3 sets here, in this case the formula ends here, but here we have 3 sets. So plus, minus, then again plus. You take intersection of 3 sets. Now you see the pattern now. Now you can easily write, although this is yet to be proved, something like this. You add the cardinalities of the individual sets. Then you subtract the cardinalities of intersections by taking 2 sets out of them. That gives you AB, BC, CD, DA, AC, BD. This many possibilities. Then after that, after having minus, you write plus. Now you take 3 sets at a time and write their intersection. ABC, BCD, CDA plus ABD. Then comes 4 sets. Now since there are 4 sets, so that is the end. Plus, we have written plus, then again minus. So the signs alternate. First you write plus for 1 set, then minus for 2 sets, again plus for 3 sets, minus for 4 sets. So this is the formula. So this way it goes. Okay. This one we have proved, this one we have proved. This also can be proved, but it will not be used. It's highly unlikely this will be used in an actual problem. Now after this will come the problems of set theory, which we will see in another video. I mean another part of this video. Okay, this is only one part. Or I think this is going to be one of the parts. Okay, so see you in the next part. Signing off.